सुस्वागतम, नमस्कार, adabas, केम छो, good afternoon, good morning, good evening, depending upon which part of the world you are. आप सभी का PRL के अमृत व्याख्यान में स्वागत है, अभिनंदन है. A very warm welcome from me, Anil Bharadwaj, for the PRL का अमृत व्याख्यान. Today is the 46th व्याख्यान of the series of 75 episodes of Vyakhyans, which is being organized as a part of PRL's 75 years of legacy and history in fundamental physics and space sciences. Established in the year 1947 by the father of Indian space program, Professor Vikram Sarabhai, the PRL's Platinum Jubilee coincides with India's 75 years of independence. Hence, it's a joint celebration of the development of science and technology in India by PRL under the banner of PRL Ka Amrit Vyakhyaan. Today, we have yet another very distinguished speaker or the Vyakhyaan Karta with us, Professor Brasseur from Max Planck Institute for Meteorology in Hamburg, Germany. And he is also affiliated with NCAR, that is National Center for Atmospheric Research in Boulder, USA. We thank Professor Brasseur for accepting our invitation and joining us in the PRL Ka Amrit Vyakhyaan, which is a part of PRL's Platinum Jubilee celebration. I now request my colleague, Professor Lokesh Sahu, to kindly introduce today's Vyakhyaan Karta to our audience on the WebEx, as well as those who have joined us live on the YouTube channel of PRL. Over to you, Dr. Lokesh.
Yeah, thank you, sir. And I'm very pleased to introduce today's Amrit Vyakhyaan speaker, Professor Brasseur. Professor Brasseur is well-known and recognized scientist in global atmospheric and climate science community. Professor Brasseur was educated at the Free University of Brussels, Belgium, where he earned 2 engineering degrees, one in physics in 1971 and one in telecommunication and electronics in 1974. He obtained his PhD degree in 1976 at the same university, but completed the work at the Belgian Institute of Space Aeronomy. Between 1977 and 81, he served as an elected member of the Belgian House of Representatives, Belgian National Parliament, and was delegate to the Parliament Assemblies of the Council of Europe and the Western European Union. In 1990, Professor Brasseur became Director of Atmospheric Chemistry Division of NCAR. He served as Editor-in-Chief of the Journal of Geophysical Research Atmosphere between 1992 and 1996, and during the period 1994 to 2001, he became chair of the International Atmospheric Chemistry Group, that is called IGEC, of the International Geosphere Biosphere Program, IGBP. On January 1st, 2000, Professor Brasseur became director at the Max Planck Institute for Meteorology in Hamburg, Germany, and honorary professor at the universities of Hamburg and Brussels. He also became the scientific director of the German Climate Computer Center. Between January 2002 and December 2005, Professor Brasseur was the chair of the scientific committee of the International Geosphere Biosphere Program, IGBP. He was also president of the Atmospheric Sciences section of the American Geophysical Union 2002 to 2004 and member of the Council of AGU. He was a coordinating lead author for the 4th assessment report of the Intergovernmental IPCC, and jointly with Al Gore, the IPCC was awarded the 2007 Nobel Peace Prize. Between January 2006 and July 2009, Professor NCAR and head of the Earth and Sun Systems Laboratory, and in July 2009 became the founding director of the Climate Service Center. that is CSC in Hamburg, Germany. Since June 2014, he is affiliated with the Max Planck Institute for Meteorology. He is also a distinguished scholar at NCAR. Professor Brasseur is a member of Academy of Europe, a foreign member of the Norwegian Academy of Sciences and Letters, an ordinary member of the Academy of Sciences of Hamburg, Germany, and an associate member of the Royal Academy of Belgium. His doctor honoris causa of the University of Paris, Oslo, and Athens, and fellow of the American Geophysical Union. Professor Brasseur has published about 200 peer-reviewed papers, and he has also published and edited several books. He is the recipient of numerous awards and honors, such as the Veterans Prize of the Royal Academy of Sciences and Letters, Belgium, Prize Jacques Cox of the Free University of Brussels, NCAR Outstanding Publication Award, NASA Group Achievement Awards in 2005 and 2009, Award on Environmental Physics from the European Physical Society, and Beat Ignacio Morena Prize in 2005. And I'm happy to also inform that one of your famous books, the Aeronomy of the Middle Atmosphere, is it is a reference book for our pre-doctoral courses in physical research laboratory. So that is Brasseur and Solomon. So with this introduction, now I invite Professor Brasseur for his talk on a historical journey to discover the mysteries of air. Professor Brasseur, please.
Thank you very much for your detailed introduction. Just shows that I'm getting old with all these past activities. But let me say that I'm really honored to be able to give you a lecture today or a seminar. PRL is always in my heart because I've been visiting there twice. I've been working with colleagues there, Sean Lull, for example, and so I'm really wishing you, all the best wishes for the next years ahead. And I know the excellent work that you are doing. I love fundamental science, and you are carrying really the example of what fundamental science should be in Earth and space science. So what I would like to do today is to give you a bit of an unusual presentation. I don't do that very often. I usually talk about a scientific issue or presentation. I present some of results. But this time what I would like to do is really to give you an historical talk. And I'm going to share my screen. Hopefully it will work. I think it does work. Can you see my screen like this?
Yes, Professor.
Okay, so I would like to do a historical journey through time and discover the mysteries of air. And the reason I'm doing this approach is because it's a nice approach to really understand the science. You see, science is not falling from heaven. It's really a progressive activity that is based on integrating previous knowledge and trying to make progress. And so let's try to make, And so I'm going to go through different periods or different issues, talk a little bit about the very early view of the Earth, and then we'll talk about the discovery of major gases, essentially oxygen and nitrogen, the discovery of greenhouse gases, discoveries about upper atmosphere, and then we'll talk a little bit about progress made in the ozone research. So let's start with the very early time. And the ancient Greeks had a view of what nature is, and already almost 400 or 500 years before the Christian civilization, they really expressed the complexity of nature by 4 substances: earth, water, air, and fire. And Aristotle added a 5th element, which was the aether. It's everything that was around the earth, something that, of course, you like to study at PRL. But of course, a number of cultures took those concepts. Some, of course, used different words, sometimes wind as opposed of air, or void as opposed of ether. The Chinese had a different way of characterizing essentially how nature was organized. And so you can see here, for example, essentially well, you see all the scientists essentially of the school of Athens that's been painted. And in fact, if you look at trying to get, okay, you look here at two of those, Platon, who is pointing to the heaven, to the sky, symbolizing the mystical aspect of nature, while Aristoteles was putting his hand towards the earth, symbolizing the realism view of nature. So there were different ways of thinking of nature at the time. And so if we look at the period ranging from that early antique Greece time to the medieval times in Europe, it was really dominated by spiritual culture. And following the fall of the Roman Empire and the decline of knowledge of the Greek, Western Europe was really cut off from important source of ancient learning and innovation. And so the Middle Age was a period of poor advancement in science. Many new ideas were discredited by the Catholic Church. Scientific experimentation and progress were really not so much pushed or encouraged. However, in spite of this, what we call dark time for the science, there were some intellectuals who were trying to move forward. And so the Renaissance appeared. The first really studies of the atmospheric composition began in the 17th century. And you had a number of brilliant minds, we will talk about them in a minute, who discover basically oxygen, nitrogen, and carbon dioxide in the atmosphere. Even though they were not using those terms, they had other terms to characterize these gases. So in the 19th and 20th century, the focus moved towards minor constituent with low concentration, including ozone, and that was discovered in 1839. And of course, today, atmospheric chemistry is really important as a contribution to the Earth system. So we have to put the chemistry, the composition of the atmosphere in a broader context of Earth system, and relation in particular with the biosphere and the ocean become very important. So let's go now to the scientific renaissance and the discovery of the major gases. I'm going to mention a name that not many of you have heard, except maybe the real chemist. This is a Flemish physician who lived between 1579 and 1644. He's seen as the pioneer in what's called the pneumatic chemistry. He introduced the word gas. Now, literature says it's probably coming from the word chaos. I don't really agree with that, because in fact they were talking about a spirit. Gas were spirit, and in Flemish the word spirit is called geest. So gas is probably coming from geest. That's what other people also are thinking. So he identified what he called the silver gas, obtained from burning and also from fermentation. And that was, of course, CO2, even though he didn't call it this way. So he believed that the gas had an origin, which was supernatural. So he was very religious in a way. It can extinguish flames. It can occur in mine and cause death. Now, death, dying, not death, it's written here. So he defined basically, this is important, the inflammable character of matter as phlogistos. And this concept will become important about a century later when George Stahl adopted it to explain combustion. So here is a picture of him. You can see one of his books that was published, and in reality, he was living at the time of Galileo, and so I called him the Flemish Galileo, the Galileo from Brabant, which is a province around Brussels where he worked. And so basically he was sentenced in 1629 by the Catholic Church for arrogance, for proximity of Luther and Calvin, who were the Protestant leaders, and he was put on house arrest until 1636. His publications were seized, disappeared, burned, but he got rehabilitated 2 years after his death in 1646. So you could see how tough it was to be a scientist at that time. Then, of course, later on, a number of people were looking at that. So there was a clergyman in England, Stephen Hales, who believes that the air has really two components: the elastic component, which is really the compressive part of air, and then what he called the fixed air, which is fixed by plant and animal. So these were biologists really looking into that. And then Joseph Blake, around the same time, a bit later, who was a professor at Glasgow, noted when you burn calcium carbonate, some gases are released, and he called it fixed air, just like basically Stefan Hales has said, which is the equivalent of carbon dioxide. So carbon dioxide was probably discovered before the major gases. But then came the phlogiston theory that was opposed to the oxygen theory. In fact, the German alchemist, who was professor at the University of Mainz, called Brasseur, he basically decided that we should replace the 4 elements that the Greek had introduced by 3 elements. Terra lapidea, the solid earth. Terra fluida, the fluid earth, so water and maybe air, but terra pinguis, the fat earth. And he indicated that combustion releases, in fact, terra pinguis. So the idea is that combustion was the release of something. And so Stahl, that I already mentioned, he took that concept, but he replaced it a bit by the fire material called phlogiston, which is believed to be included in all the component that burn. So wood, coal, iron, those things burn, they release during combustion. So they must be included in the material. And if there is combustion, it's because this material is included. That's the phlogiston theory. It dominates science until the end of the 18th century, and you see me here writing his book. Now, at the same time, everybody was convinced that phlogisticated air was important, but some progress was nevertheless made. Rutherford, for example, what he tried to do, he was a firm believer in the phlogiston theory, and so he eliminated the oxygen, the air that was basically burned by a candle in an enclosed vessel. They put a mouse to see when the mouse was dying. Then they said, okay, this gas is gone. Then there was some resulting air, and he removed the CO2. And then he said there is something removing noxious air. They call it also phlogisticated air, and that was essentially nitrogen. So he found that it was a second component. He didn't know what it was, but he called it phlogisticated air. And of course, this is nitrogen. So, by the way, Cavendish, who was a very interesting personality, a very shy person, he almost published nothing because he was afraid to publish. He was afraid to talk to women. He even had a secret stairs in his house so that he could move upstairs without encountering the servant, in particular the female person. So he basically did excellent work, but not really published. And so he found out that phlogisticated air account for 21% of the common air and dephlogisticated air for 79%. But what he noticed, what was very important, is that about 1%, 1 out of 120 of the volume remained unexplained and unidentified. So we'll have to wait 2 centuries to find out what it was. Okay, then, you know, John Maddow talked about active air and inactive air. They call about spiritus ignio aerius in Latin. This is the air that contributes to combustion and respiration. So you can see they're not calling anymore for phlogiston included in the burning material, but they're talking about air that is facilitating combustion. So we're moving slowly towards the oxygen theory. And then Carl Wilhelm Scheele, who was a pharmacist in Sweden, was talking about fire air, so the air that is producing combustion, which is oxygen, of course, and then noxious air, which was the nitrogen. So we're moving towards oxygen theory. And it is, of course, Priestley, the British religious leader. He was also a dissenter compared to the British, to the English church. He contributed really to the theory of oxygen, but he never rejected the phlogiston theory. He measured a number of gases, nitric oxide, ammonia, he discovered them. Nitrous oxide, he was able to isolate oxygen, and he published his results in 1974, 2 years before Shale published his discovery of that. So he was first to publish, but Shale was probably the first to discover. Now, Priestley was an interesting personality. He supported the French Revolution, although he was in England. He supported the American Revolution. So people were very, very upset on him in England. And so in 1971, he had a big banquet to celebrate the Bastille Day, the revolution in France. And during that banquet, a number of people came to burn his house, and he started to be in trouble politically. So he moved to the US, where he became a church leader, and then finally he died in Pennsylvania. So, but Priestley also visited Lavoisier, Antoine Laurent de Lavoisier, who was a real great French scientist, and essentially Lavoisier did quite a bit of study. He arrived to the same conclusion as Priestley. He repeated the experiment that Priestley did, but he was contrary to Priestley. He strongly rejected the phlogiston theory and replaced it by what he called the oxygen theory. He introduced the concept of mass conservation in chemistry, which was very, very important, and introduced modern nomenclature for the species. He introduced the word oxygen. For example, we see him as the father of modern chemistry. You see him on the plot on the right, the picture with his wife. There, his wife was playing a major role. She was helping him in the lab. She was also drawing, and you see on the left a drawing of an experiment about oxygen. You see on the extreme left a person who is trying to breathe the air, and you see his wife on the right who is taking note of the experiment, but she was also the person who was doing the drawing, in particular the one you see here. And she knew a lot of languages and was translating for him a lot of the books that were published, in particular in English. Now, Lavoisier was also what was called a fermier général, which is a person collecting taxes for the King of France, Louis XVI. He was getting a portion of the taxes, so he was rich. It allowed him to develop, of course, his lab with all this money that he had been gaining. But he got in trouble with the French Revolution. He got arrested in 1793. He was put in jail. He was sentenced to death by the Revolutionary Court. You see here the trial. And he was executed, guillotined with other fermiers généraux a bit later. So he was saying, you know, why can't I just live a little longer and finish my experiment? Somebody in the court said, we need him. He's such a great scientist. And the judge said, the revolution doesn't need scientists. So it is, you know, something that we have heard in the world several times. But this is then his book. He wrote an elementary chemistry treatise that was very, very much the fundamental aspect of the modern chemistry. So I mentioned that when people were looking in Cavendish in particular, found out that there was 1% of the gas that was missing, not explained. And that was finally solved in the 19th century by essentially William Ramsay. And they discovered then what they called argon, a gas that had no reactivity. They also discovered the other noble gas present in the atmosphere. So that's been a long story to get the major constituent of the air. But now we go to the greenhouse gases, and we go backwards in time a little bit, when a Swiss person, Horace Benedict de Saussure, went He tried several times, he failed, but finally he got there. He went to the top of the Mont Blanc, which is the highest mountain in Europe, and he took with him what he called a thermoscope, which you see here in the middle, which was a box with 3 glasses called vitre. You see vitre, that's French. And he put 3 thermometers inside, and you can see the value of the thermometers. The one that's the most internal to the box was the warmer, and so the energy that is absorbed by the box through the glass, solar energy goes through the glass, is absorbed by the box itself, and it releases then some what they call obscure heat, and that it seems that this obscure heat is trapped inside the glass ball and warms the internal part of the box. Now, he didn't understand exactly what was happening, but maybe I forgot to say, Fourier, you see him on the right, explained that and he drew a parallel with the atmosphere. He said, well, exactly what I just tell you, solar light is not absorbed, penetrates in the box, and the obscure heat, which in fact is infrared radiation, is trapped into the system. That must happen also in the atmosphere. And so the concept of greenhouse effect came out, although Fourier never used the word greenhouse effect. That came pretty later. Now, in 1859, John Tyndall, kind of a British scientist, measured the absorption of the obscure radiation by CO2 and by water. He developed this instrumentation that you see here. And there was enough information for Svante Arrhenius, who was a well-known established scientist in Sweden, to highlight the importance of CO2 in determining the temperature of the Earth. And so he concluded from his studies, here's his paper, on the influence of carbonic acid in the air upon the temperature of the ground. He said if the level of carbonic acid increases geometrically, the temperature should increase quasi-linearly. He calculated that the doubling of CO2 would lead to about 5 to 6 degree warming. That's interesting because now with all the complex models, we find the same results essentially. So that was already there. However, the experimental measurements that I mentioned, including from Tyndall, suggested that most of the greenhouse warming is not coming from CO2, but it's really provided by water vapor. And so the interest that after the paper by Arrhenius, the interest in CO2 vanished. It appeared that, the CO2 was not a problem, that everything was due to CO2, and some controversy already started at that point. Now, a bit later, 1938, a steam engineer, good Guy, in fact, English, Guy Callender, he was interested in climate. He was not a climate scientist, he was a steam engineer, but on the weekends, in the evening, he started to look at all measurements of temperature, and he found out that between 1890 and 1930, the temperature had been increasing about everywhere in the world. And he said, well, wait a minute. The only thing that is really changing is CO2. So CO2 should play an important role. By the way, it's important to say that at that time, there were other considerations. So the Austrian geologist Suess introduced the concept of the biosphere. And then the Ukrainian-Russian scientist Vernadsky took that concept and popularized it. And so it appeared that, the biosphere is also affecting CO2, not just the anthropogenic emissions. In 1957, Revel and another Suess, it's a different one, highlight that part of the CO2 is absorbed by the ocean. And so the greenhouse problem became an Earth system problem. It started in the atmosphere, but it shows the influence on the entire Earth system, including on the climate system. So one person said, I need to understand all that. And so during the International Geophysical Year, Charles David Keeling, established with the help of NOAA, in fact, which was not called the Weather Bureau of the US at the time, established at Mauna Loa a station that would measure CO2. In fact, they put also some instrument on aircraft at that time. And you see at the top graphic, the first measurement of CO2 made at Mauna Loa and from aircraft. And they all showed in the Northern Hemisphere a seasonal variation that you see here very well represented. Since then, the measurements have been continued. A lot of problem for Keeling to get the funding, but you see this seasonal variation still visible. But at the same time, we see an overall trend. So clearly CO2 is increasing. And there's been a lot of interpretation to see how much of that gets in, how much of the CO2 emitted gets in the ocean, how much is captured by the biosphere. But that was the beginning of a beautiful monitoring aspect that serves us very much. This is the station of Mauna Loa. You see it's about 3,500 meter altitude in Hawaii, far away from the sources, so you get really background value, and very often you are above the clouds. Now, CO2 is one gas, but there are other ones. Another one is methane. And methane has been discovered by Volta. Volta, you see him, was on vacation in the Como Lake, and there were marshes, and he saw that there were bubbles coming out of the water. And you see him here in his boat, he's capturing some of the bubbles. He analyzed them in a lab, and he found that this air was explosive. That was the discovery of methane. But he didn't call it methane either. He called it marsh gases. And it is only around 1950 that a Belgian scientist who was visiting Hawaii and was working there, I think on his postdoc, he was measuring the solar spectrum. So looking at the sun, he didn't care about the atmosphere, but he found some lines that he could not really explain, and they were exactly the line expected from methane. And he concluded that methane must be present in the atmosphere, and then making big trouble in his measurement of the solar spectrum. There was some absorption by methane, and then it initiated some studies, in particular from Jungfrau-Joch station, which is also above 3,000 meters in the Alps, a very beautiful site. You can go to the top there by train, and if you are in Europe, I would recommend you go to Jungfrau-Joch. It's open to tourists. You just have to take a train that goes into a tunnel up the mountain all the way to the top. Now, another gas, nitrous oxide. So it was already synthesized by Priestley, by the British scientist Priestley, but some people started to see that this gas had maybe therapeutic property for pulmonary diseases. And people started to look at this gas very clearly. They found that this gas had also making you laugh, hilarious effect. And so a young chemist called Humphrey Davy, who became, by the way, president of the Royal Society, he just himself tried to absorb in his body N2O to see if he would go crazy. And you should read what he felt at that time. This is, he wrote about this. This is very important. What is important to know is that laughing gas were used then in parties in London by high society to really have times where everybody was laughing, having a good time. So you can see here Davy, who is trying to inject some laughing gas to this woman. The first one already got it, and she's smiling. And so you see that it was a time. But so was it present in the atmosphere? Yes. In fact, in 1939, there's an astronomer who was in Arizona at the Observatory of Flagstaff, Arthur Edel. He was getting laughing gas from the local hospital. So that helped him to get a spectrum of N2O. And he found out that there were some lines in the, also in when he was measuring the solar radiation, the spectrum of the solar radiation, he attributed some lines in this, but they were very difficult to detect because they were shadow from water vapor. And it's only because he was in Flagstaff, where it's very, very dry and the water vapor is very, very low, that those lines could appear. So, but he detected N2O as so 1939, so not too long ago, as a permanent gas of the atmosphere. Okay, now a quick discussion about the upper atmosphere, which of course has been very, very much in the agenda in the last century. So what was the view of the upper atmosphere in the early 20th century? You see here two graphs that I found. On the left, you see the level of assumed level of azote, which is nitrogen, and the level of hydrogen. This is from a French paper, as a function of altitude. Altitude is around the X value here. And so you can see that near the bottom on the left, so nitrogen is about 80%, and he assumed that it's decreasing and is getting to zero at 100 kilometers. On the other hand, hydrogen was zero at the surface, increases and gets 100% roughly at 100 kilometer altitude. And so at 80 kilometer altitude, both nitrogen and hydrogen seems to have the same amount. Of course, we know it's not true. It's interesting to see that, for example, at 30 kilometer or 40 kilometer, they assumed that 10% of the air was hydrogen. So that was a false view. Another view, which is a model now from Chapman and Milne, showing the mixing ratio of the different species. And here they do not talk much about hydrogen, but they talk about helium. They believe that the mixing was only happening below 20 kilometer. So we know now that species are mixed up to 100 kilometer altitude. So in the 1920s, we still did not know very much. Here he assumed that in the upper atmosphere, everything is covered by helium. And so it is very different. So let's see exactly what happened. Now, people have used, of course, we had no satellite, we had no rockets, we couldn't get to the upper atmosphere, no way. So we had to find another way to get information coming from up there. One of them was, of course, aurora. People have already been fascinated by aurora, and in fact, we had to explain how the aurora were formed. And so Vyakhyaan, before around 1900 in Norway, he had organized several expeditions in polar region to study the magnetic field, and he developed a model, a physical model, not a mathematical model, a physical model called Terela, by creating a magnetic field and injecting cathodic rays in the field, so electrons. And he found out that the electrons would really converge in the polar region and basically accumulate around the magnetic pole. So that was exactly what the aurora were doing. So he said, okay, aurora are affected by the magnetic field of the Earth, but still we don't know what it is. So aurora are beautiful. They are there because of the magnetic field. So Angstrom, you see Angstrom here, he detects, well, you don't need a spectrometer, but that there were green aspect to the aurora, and in particular, a green line. So it took about 40 years to identify what this green line was. People thought that it was helium. People thought that it was all kinds of things. People thought that it was maybe chemical compounds that we had never discovered, called the coronium, etc. But it's finally, and I don't have time to go into that, but it's finally two scientists at University of Toronto who found out a bit by accident that the green line is in fact related to a forbidden transition between two states of the oxygen atoms. And you see it here. You see the fundamental O triple P, you see the singlet O single D and the singlet O single S. And the line, the green, I'm sorry, it's in French, but the 55.7 nanometer is a transition between O single D and O single S and O single D. And in fact, what you see in red sometimes in the sky is then a transition of O single D to the fundamental O triple P. So it took about 40 years to discover that. And it was only possible because fundamental molecular physics or atomic physics and spectroscopic physics have made so much progress. And you know, it's because the fundamental knowledge was not there that it took so much time, but finally it was solved. By the way, in 1948, Milne, Aidan and his wife, both astronomers in the Western US, they looked also at the air glow and the emissions by the sky, and they discover what's called now the minor bands, emission by the hydroxyl radical OH in the upper atmosphere. So all this information told us that there were atoms and there were radicals in the upper atmosphere. So that's how they got really information. And then with the aid of models, they started to look at the possible vertical distribution of all the species, learning a lot about molecular diffusion, distribution. The lighter species like helium and hydrogen become important, not at 50 kilometer, but maybe 800 or 900 kilometer altitude. So a lot has been learned from the spectral analysis of what we found in the atmosphere. So that's one way. Another way was to look at the investigation, basically, of the upper atmosphere by sending electromagnetic radiation. And of course, you know that Marconi, in fact, established the first radio transmission between the American continent and Europe around 1902, 1903. In fact, he was able to send a message from Roosevelt, the former Roosevelt, Theodore Roosevelt, and King Edward VII in the UK. He got a big reputation because his radio transmission helped to save passengers on sinking ships, including the Titanic, in the North Atlantic. So he got a great reputation. He became senator. He supported, unfortunately, Mussolini after that, and so his history is a bit affected by that. But basically what happened is that Kennelly and then Heaviside showed that the only way you could do this transmission that Marconi had been doing was if you had a layer that would reflect radiation, in the electromagnetic radiation, and that implied that there would be some kind of electrical current happening in the atmosphere, and therefore you needed to have essentially electron at that level. And so around 1903, Taylor suggested that the electric charges that constitute this reflecting layer result from the photoionization of atmospheric molecule and atoms by solar variation. So a very important name in the research of the ionosphere is Victor Appleton. He made measurements. He found out that the layer, this reflecting layer, was located at and above 100 kilometer altitude, and that gave him the Nobel Prize in Physics in 1947. Finally, let's say a word about ozone. Now, ozone, as you know, has been very much on the agenda at the moment, but it was discovered already in 1839 by Christian Friedrich Schönbein. This was a German professor acting at the University of Basel in Switzerland. And he had been doing electrolysis of water in his laboratory, and he started perceiving an odor at the positive electrode. And so there was a lot of discussion to see what it was. And we had to wait a long time before essentially the nature, the fact that it was a gas that was released by the electrolysis of water. There was a lot of discussion happening. Not everybody agreed. Some people said, well, it should be a form of oxygen. And then, yes, they moved toward that direction. Now, finally, for example, Schönbein believed that it was an ionized form of oxygen and a negative form of oxygen. And so if there was a negative form of oxygen, there needed to be a positive form of oxygen to maintain electrical neutrality. And when you did all that, you realized that you had to create another species than ozone that was positive. And that was called anti-ozone. But finally, it was indicated that ozone was 3 oxygen atoms. And that came, in about 30 years after ozone was discovered. So ozone was discovered in 1839 And 30 years later, it was assumed that it was 3 oxygen atoms. So ozone is oxygen dioxide, essentially. In 1858, a professor in France, in Rouen, an agricultural professor, he made some measurement of ozone, and he realized that ozone was a permanent constituent of the atmosphere. So it started to be measured all over the place. And this is now 2 measurements. On the left, in Germany, in Emden at the coast, and they started to see some kind of annual variation, seasonal variation. In Paris, they were measuring ozone at different streets, different locations, and they found that the value were pretty different. The units, sorry, the units was not ppm or ppb, but was just the indicator of a piece of paper that was used to detect the presence of ozone in the air. So there was a scale that Schönbein had introduced, and the more blue the paper was becoming, the more ozone was present. So the idea was, okay, where is ozone located? And so in 1913, Fabry and Buisson in Marseille built a spectrometer, and they measured the solar radiation and saw that there was an absorption really taking place below 300 nanometer in the ultraviolet. And so they had measured in the laboratory that ozone was absorbing at wavelengths smaller than 300 nanometers. And that led them to provide an idea of what the ozone column was. And so they concluded that the ozone column first was about 5 millimeter. And then after World War I, they redid the measurement, and they say, no, it's not 5 millimeter, it's more like 3 millimeters. So we have a very, very thin layer of ozone. If it was pure ozone, it would not be more than 3 millimeter, but nobody knows at what altitude ozone is located. So everybody started to think more about the column, and Dobson in 1924 built spectrometers. Those spectrometers were sent all over the world. You see here on the right, the first spectrometer that he built. That's now in Oxford, in the museum, in the school. And you can see that they started to have information about the seasonal variation of the ozone column, but also the latitudinal variation, going from Egypt, California, all the way to very, very far north. And they could see that ozone was maximal in spring and at high latitude. And in the southern hemisphere, they could see that the maximum was more like in September, and that the annual variation was much larger at higher altitude. But they couldn't explain it at that time. So they were also trying to do some vertical measurements. And in fact, they kind of invented, in fact, maybe I can go immediately to the next slide, where Götz invented in 1929 what is called the Umkehr Effect to derive information about the vertical distribution. And the first study that they did, I don't have it here, but they thought that the maximum ozone was located around 50 kilometer altitude. Then Götz went to Spitsbergen in high latitude to have better conditions, higher solar zenith angle to really have a better view of the ozone layer. And then he detected that the maximum was more like 25 kilometer altitude. By the way, the Umkehr effect has been used a lot in India, in Pune and other places, and it has been widely used. We have a lot of data over India due to the Umkehr effect. Now, Umkehr effect is indirect, so the idea was to try to get it from direct measurements. So Regener, Eric Regener, and his son Victor decided to measure the solar ultraviolet radiation from Stuttgart in Germany, southern Germany, in 1924. And you can see here the spectrum that they observed during the ascent of the balloon and the descent of the balloon. On the right, you see the total amount as a function of altitude. They could calculate the derivative of that and get the vertical profile of ozone. In the US, they wanted to have a manned experiment called Explorer 2. There was an attempt, Explorer 1, that failed. The balloon blew up. The gondola fallen down, but with the parachute, the people had parachutes, so they had to jump from high altitude in the atmosphere, and they were rescued. They started in 1935 again. This was the second attempt on November 11, and they were able to reach 22-kilometer altitude. And you can see here the first vertical profile that came out of those direct measurements. So what you see called RR is the measurement of Wegener that I showed you earlier in Germany. And then what you see A and B are the manned balloon, the Explorer experiment, showing a maximum of ozone near 22-kilometer altitude. Well, Wegener showed it at 25-kilometer altitude, 26-kilometer altitude. So around this time, we started to have an idea about the vertical profile. By the way, Wegener, who had sent this balloon, wanted to take advantage of the V2 rockets that the Nazis had been developing before World War I, or during World War I, in fact, World War II. And they started to build an instrument called the Wegener barrel. In German, they say Wegener Tonne, to put on the rocket, and with the idea of going up to maybe 100 or more kilometer altitude and measure ozone by rocket. But when they wanted to launch, they were rumored that the Soviets were coming, the tanks were coming. And so Wegener was being sent away from the place where they were launching rockets. And so his instrument was really never finished. It disappeared. And in fact, it had been tested a little bit in January 45. A bit earlier, but not really. The instrument disappeared, and by the way, was found back in the US at the end of World War II. So the rockets were also transferred to, the V2 rockets, the German rockets, were transferred to New Mexico. And so the Americans did a number of measurements of the solar ultraviolet flux, and they were able to get vertical profile of ozone. You see here a rocket in New Mexico now, not in Germany anymore. Before the start and after it collapsed, they tried to get the instrument back and reuse it. And you see in the middle the UV radiation that is measured, and then the vertical profile that is determined. One point also to indicate that, of course, we needed to know how ozone is produced, and it was done in a conference in Paris by Sidney Chapman, who introduced the first scheme that described the photochemistry of ozone. I don't have time to talk much about it, but of course, we know that this scheme is still at the basis of ozone today, except that the last reaction, O plus O3, is too slow to explain the observation. And so some people have shown that this loss can be catalyzed. So Nicolay and Bates and Nicolay, showed that this last reaction, O plus O3, can be catalyzed by the OH radical. So he showed that in 1950, 20 years after Chapman had discovered his scheme, or presented his scheme. But that occurred essentially in the upper atmosphere, in the mesosphere. And this was kind of related, 1950, to the discovery of the minor bands of OH that let Bates and Nicolay believe that OH was present in the upper atmosphere. Now, 20 years later, again, Paul Crutzen showed that nitrogen the loss of ozone was catalyzed by NO. And of course, that opened, another big important aspect for the stratosphere, because it is the major loss of ozone in the stratosphere. 4 years later, Stolarski and Cicerone showed that catalytic destruction can take place with chlorine. Where is chlorine coming from? They first thought maybe from the space shuttle, maybe from volcano, maybe from the ocean, but it is really something that was affected also by human activities. And so the chlorofluorocarbon came in the picture. They were measured for the first time in 1971 by James Lovelock, who was on a cruise, and he showed that there was more CFCs in the Northern Hemisphere than in the Southern Hemisphere. It was on the cruise in the Atlantic. You see him here. And 3 years later, in 1974, Molina and Rowland said, well, those chlorofluorocarbons could be produced by industry, and it could be the largest source, and it could deplete ozone. So a lot of discussion until 10 years later, Farman and in the UK and Chubachi from Japan showed that ozone was really low in the polar region. You see the curve on the left at Halley Bay Station, where ozone, which was around 300 Dobson units, this is October, in the 60s was only about 100 to 150 Dobson units in 2000. So there was really something happening. And here is their measurements. I mean, this is kind of the graphics paper where they were measurements. You see it starts 1957 all the way to 1984. This was their data, their raw data. By the way, a little bit later, NASA found out that, yeah, satellite can see it. P.K. Bhatia took Nimbus 7 Tom's ozone, and you can see the first ozone hole here that was reported. They hadn't measured it earlier than the British, although they had it in their data, but they were not sure. And they were thinking that maybe it was an artifact, so they didn't want to release anything. But finally they did. The explanation for the reason of the ozone hole came from Susan Solomon and colleagues, Orlando Garcia and Encar and Wobbles and Rowland himself, proposing that chlorine be activated on the surface of the tiny particles that constitute stratospheric clouds that are present in the atmosphere, which had been observed. And so there was a lot of work done, initiated by this proposal, to really understand what was happening in the laboratory in particular, but also field campaign that took place in Antarctica. And they really confirmed that chlorine was extremely high there in sufficient amount to destroy ozone. These are polar stratospheric clouds already observed in Norway in 1929. That has been observed only certain years, so every 20 years you see those. And so we knew that they were there in the south, certainly, but sometimes also in the north, so that sometimes we have, it's really cold in the Arctic, also some large ozone depletion. And that gave the Nobel Prize to Paul Crutzen, Mario Molina, and Sherry Rowland in 1995. So these are big successes for our community. And here you see a more recent 2003 picture of the ozone hole, which is now covering the entire continent. So thank you very much. This was a bit long, but I think I went through a lot of material, and I will be happy to answer your question.
So thank you, Professor Brasseur, for very interesting talk and presentation, and also for taking us through an excellent and memorable journey to discover the mysteries of air. Now for question answer and discussion session, I invite our colleague Professor S. Ramachandran. Ram, over to you.
It was a fascinating journey of air composition and the kind of research that went into the last 3 centuries or so. I'm sure there are several questions, I think, as an outcome of this interesting talk. Questions are welcome. Any questions from the audience?
It's very difficult to ask question on historical presentation. You know, if I gave a science presentation, people say, "Oh, I don't agree with this. This is really a mistake," and then I would have to argue. But here, it's more like, you know, when you read a book, you see how things are going. So if you feel that you want to look at the presentation later on, and you can always contact me by email.
Yeah, Professor Ram, can I ask the question?
Yes, please go ahead.
Yeah, thank you very much, Professor Brasseur. This is a really very interesting presentation and study of not only atmospheric science, but basically the scientific method, the beginning of science, scientific method and culture. So in this context, I would like to add regarding the contributions of Professor K.R. Ramanathan. So, I mean, the first director of PL. I mean, he was the person who did a lot of research in ozone, and also, I mean, the sounding rockets, all those things, and Dobson spectrometer, which you mentioned, and he was the person who installed those instruments in India from Indian perspective. Would you like to comment on that?
No, I know. I have not been talking yet. I'm still, all this is in the making at the moment, this presentation. So I am still trying to collect information, and I want to go beyond what is known by most people. And so I'm just like I did, I have a book on the history of ozone. And in reality, there is a lot of contribution. Ramanathan is certainly one of them. And you had also a strong ozone program that I mentioned in the other book, which is, by the way, published by the American Meteorological Society. And you had a lady who a name just go out of my mind, but she was a very, very strong personality, and she was really leading. In fact, I have a picture of her in this book. She was leading basically ozone measurement aspect. Mani, her name was Mani. Yeah. Yeah, and she was doing great work. So, if you can help me, it would be great if you could give me a bit of material about what has happened in India, because I would be, I'm kind of putting all that in a book, which is not finished and working on it. And I would be very, very pleased if you could give me some information, including photos and pictures.
Yeah, we'll
on what happened in India, because difficult to find. And by the way, it's the same thing for China. There are a lot of things happening in China, but it's very difficult to reach information about this.
Yeah, we'll help you. We'll help you.
Yeah, that would be really great. That would be
and rich history of PLL, definitely. Thank you, sir.
Any other questions?
Yeah, can I ask?
Yes.
Oh, thank you so much, Professor Brasseur. It was really nice journey what you showed. One thing I missed here means you didn't talk anything about the history of aerosols. When the importance of aerosol has been recognized, and those things I missed. Would you like to comment something on that?
Yeah. So aerosol is very important, and in particular the work of Junge, but also the chemistry of precipitation that is related to that. And of course, it leads all us into, I haven't been talking about how human have changed the atmosphere, because I mean, all the issue of more particle in the atmosphere, etc. I have not yet, here is my book that I'm putting together. I've reached chapter 9. I can tell you chapter 10 is called Aerosol and Acid Rain. And chapter 11 is Influence of Human Activity. So I'm going to start working on the aerosol part. Of course, I have already some good documents, but I chose not to talk about it here because, as you can see, I had already a lot of material to disclose. But yes, the aerosol is another big part for the next talk, maybe.
Thank you. Yeah, we will wait for that.
There is an interesting question in the chat box. Sita, the person who is asking, did the discoverers of ozone hole also share the Nobel Prize?
No. No. And that's a good question. Who are the discoverer of the ozone hole? I mean, clearly the first one who reported it was Farman. So Farman and his 2 or 3 British colleagues from the British Antarctic Survey. Now, I can tell you a little bit of a story about that. You know, they were seeing the ozone decreasing in October. And you saw this graphic that I showed done by hand. So the first interpretation was that maybe the instrument is drifting. Now, they had an instrument down there in the Antarctic, and of course, nobody was caring very much about the Antarctic, you know. So why should they put a new instrument? I mean, this instrument is there, it's doing its job, nobody cared. But Farman, who was going there, said, well, maybe it's the instrument. So he brought another instrument for 2 years. And he found out that the two instruments were providing identical value. So he started to think that maybe it was observed. And this was the time also when Molina and Roland had said CFC. So, he said, well, he had an explanation, which was wrong, but he had an explanation. So then he said, okay, I should probably publish that. But his management said, no. You know, I mean, if this is true, this is terrible. And if it's not true, then we will look very bad here. So I don't want you to publish that. So he had to wait a little bit. So he wrote to NASA and say, did you by any chance also see that? But he wrote to the wrong department. The department was launching balloon sondes. And so NASA responded, we're not launching balloon sonde anymore. Sorry, we cannot answer your question. So he didn't know. Finally, he decided to publish his paper. He published it, the data were right, the explanation was wrong, but it created a big confusion in the community, and the people started to think about to explain it. There were 3 or 4 explanations. The meteorologists said it's meteorology, it's nothing else. Some people say it's, and even Crutzen believed that it was NOx coming down from high up. And Susan Solomon then came up and, she put 2 ideas together that maybe, I mean, Roland had said that if HCl and ClONO2 react together, that would create a big amount of ClO that would destroy ozone. But in the lab, they don't seem to react together. So luckily. And then other people were measuring PSCs, polar stratospheric clouds, and say, well, but if the reaction occur on the PSC, that's what Susan Solomon invented. So if somebody should get the Nobel Prize, probably her for that discovery, in addition, probably to the people who have done the measurements. But Farman died. Choubachi, had a poster with the data in a meeting in Greece. Nobody paid attention to it. And of course, after Farman discovered, so he went back to his poster and said, look, I had it also. So he also discovered it in a way.
Okay, thanks for the interesting nugget. Harish has a question.
Am I audible?
Yes.
Yeah, I can hear you.
So one of the discovery you mentioned about the hydroxyl radical in upper atmosphere. Now the hydroxyl radical is so difficult to measure at modern instruments now because of its very short lifetime. And at that time, expecting it to be in the atmosphere, what was their motivation? Why they went for looking for the OH?
So the sound coming from your computer is very, very bad. So can somebody just repeat the question for me?
Yeah. Can you repeat it, Harish?
Yeah, just try.
No, I don't hear you at all.
Harish, can you repeat the question, please?
My question was about hydroxyl radical, OH, discovery of OH in upper atmosphere. Is such and difficult to measure. My question is, what lead them to go looking for it? What was their motivation?
So you're talking about OH in the upper atmosphere. Is it difficult to measure?
That's right.
Okay, so first of all, I should tell you that there are some measurements of OH in the stratosphere that have been made, but when it was discovered, it was higher up in the thermosphere or the upper mesosphere. And so, what has happened really is that nobody believed it's there. Nobody knew what it was. But then the minor people who were interested in air glow and night glow, started to measure, what they were seeing coming down as light from the sky. And so they saw lines, so they tried to identify those lines. And so they were working with spectroscopists and people interested in fundamental physics. And so they realized that there were some lines that correspond to OH. So probably there was OH up there. They didn't know exactly at what altitude. But they knew that the night glow was coming from high up. And so it is then Bates and Nicolay who, start thinking, say, OH. I mean, especially Bates was a fundamental physicist. Nicolay was more like an astrophysicist and an atmospheric scientist. So they said, well, could OH be produced? Well, maybe by photolysis of water. And so they did a simple model. They knew the absorption in this range, how water would be photolysed. And so they introduced the concept that, there could be some free radicals in the upper atmosphere. That's the first time that free radicals were really introduced. So this discovery was very important. And Nicolay did not really insist on the impact on ozone and atomic oxygen, because, it was more like, we have to explain the bands that we observed, and we have to show that OH is there. And then, of course, Chapman has introduced the atomic oxygen. So the two came up together, atomic oxygen and hydrogen work together, react together. And so it was consistent with observations made in the aurora, in the air glow, in the night glow, etc.
Your talk was hosted both on WebEx and also in YouTube. There were participants attending on both the platforms, and I think there are participants in YouTube who would like to ask questions. I request my colleague to continue with the question answer session from YouTube. Navinder?
Yeah, so there is no more question on the YouTube.
I saw a hand raised by Professor Sareen earlier.
Yeah, WebEx panel, yes, there is.
Yeah, Professor Brasseur, good to see you again on the PRL platform.
Okay, the sound is very,
can you hear me?
Yeah, more or less.
Can you hear me? This is Sareen, and good to see you again on the PRL platform.
So what is your question?
Yeah, I was trying to understand from your historic perspective that where does the concept of where and when does the concept of the downwelling of ozone from this stratosphere came into picture in all this historical perspective which you talked about? How does these concepts were further evolved then?
So you're talking about the penetration of stratospheric ozone into the troposphere. Is that what you're talking about?
Yes.
Yeah.
Yes.
So
yes.
Regener, you see the guy with the rockets? He, in 1934, he highlighted that. He said, it seems to me that there is a strong gradient. And so he had some measurements of low value in the upper troposphere and higher value in the stratosphere. So he said, if we have downwelling, there must be introduction. And since at that time, they didn't know how ozone was produced in the troposphere, they knew it could not be produced by O2 photolysis because the light is absorbed. So that they said, well, it must be coming down. And that theory has been going on and going on as the key and the only source until 1973, when Chamidis and also Crutzen said, no, there can be also production. And in fact, the photochemical production is much higher than the intrusion from the stratosphere.
Okay.
So I see that.
Okay, thanks. Yeah, thanks very much.
Yeah, thank you. Vinet has a question.
Yes, so thank you very much, Professor Brasseur, for such a nice talk. So my question is regarding the the ozone hole and the Montreal Protocol that followed. It was ratified by all the UN members, and so it could be treated as one of the most or the most successful treaty that has. It is difficult to bring different people together, but I just want to know why this treaty was so successful in bringing everybody together, and so what were the factors that made this treaty so successful?
Yeah, I think that's a good question. Of course, sometimes people ask also, why don't we do that for climate? But of course, the climate issue is much more complicated. So the CFC issue is relatively simple. Only 10 companies were producing this material, these CFCs, and so it was just a matter of deciding to tell those 10 companies, you stop, you cannot do that anymore. Now, what I think has been the term very, very important is the attitude of the US. I still remember the discussion that took place at that time. The US under the Bush father administration, and probably with the contribution of Bob Watson, who was at NASA and was managing the project. Bob Watson convinced a lot of people that CFC should be reduced or even banned. And so at one point, there was inside the US the discussion, and DuPont, which the biggest company, decided to say, okay, we're not going to produce CFC anymore. We're going to work on alternative products. That was sufficient for the competitors to say, okay, if DuPont doesn't do it, we will not do it. But I remember very much there were discussion also. I was once at a meeting in Geneva at the UN, and the US announced that they would ban CFCs and they would stop making CFCs in the aerosol cans immediately. And the Europeans in particular, well, the Europeans were divided between the North and the South. So France wanted to continue, Italy wanted to continue, but England also, because Thatcher was there and she was, but then they changed their mind. And the Nordic country, Germany, and the Nordic country decided they would ban the CFCs also. So finally, looking at what was happening in the US, looking at what was happening in many countries, including Germany, and then having only a few companies in Italy and France remaining, they had no choice than to follow the rule. Now, it was a bit an issue for the companies are big companies like DuPont, huge company, and they are basically developing the raw product, and they sell this product to the aerosol company. They put it in the aerosol can. So the big company gave those small companies first a wrong message. They said, don't worry, we're going to convince the government that we can continue. And then suddenly they changed their mind and they said, oh, yeah, we changed our mind. We're not going to provide you with CFCs. And those small companies got really in trouble because of that. Many collapsed. All right.
Okay. Yeah, thank you very much.
Any other question, or are we concluding?
Yeah, so I think we are moving towards concluding.
There is one more.
There is a question on chat box.
On chat box, okay.
Somebody was asking for reference, I see.
It would be.
Let's see here. I would, if you could mention some of the reference for further reading. Yeah, I have a list here of papers, but I would suggest that Imran sends me an email. I'm going to give my email here. Oops.
We should actually wait for your book.
Yeah. There is a book. I'll give you. Okay, Let me just put my email, one of my private email here, in fact. So this is my email. You can ask me more questions by email on that. And so my book is, well, the last book is on the ozone layer. And it's American Meteorological Society. So you can Google it. It's about 2 years old or something like that. So it says from discovery to recovery. Let's go from discovery to recovery. And if you don't find it, let me know. I'll give you more detail.
Okay, Bhushit.
Yeah. So we are coming to an interesting talk. Thank you, Professor Brasseur, for sparing a time for us and having this wonderful talk. It was a classic talk to teach us that how to narrate the evolution of science in terms of putting facts and interesting information. It will be a great value addition to our Vyakhyaan series, and this will be available for anyone to see anytime on our YouTube channel. Once again, thank you. Thank you, Professor Ramchandran, for conducting the session. Dr. Navinder Singh also to conducting the session. We thank all our viewers who joined us on WebEx as well as YouTube for this talk. We extend our thanks to our director, our dean, and the Vyakhyaan committee for extending all their support anytime and every time we need that. Please stay tuned with us. Next week, on the occasion of International Yoga Day, we are coming up with a very nice talk by Sri Atul Karwalji. So we look forward to have you again with us. Till then, take care. Bye-bye.
Thank you.
Thank you.
See you
And
again.
best wishes to all of you.
Thank you.
Bye-bye.
Bye-bye.